Okay, this is lesson 1, the concept of instantaneous rate of change. And here the big idea is we're going to talk about instantaneous rate of change and average rate of change. So here it says the average velocity over some given time interval can be defined as the ratio of change in position over change in time period. And we rewrite that as the change in distance. So distance can be exchanged for the word position over the change in time, or we just simplify this saying the change in d over the change in t. So that's average velocity, and then what do we mean by instantaneous velocity? So this is the speed and direction of an object at a particular moment. So think of time being one spot, so like t equal to 5. It says, can you explain why we can't define instantaneous velocity as a ratio? Well, if we try to identify this as a ratio, think of almost like average velocity and instantaneous velocity as slope. So let's say we had, using our slope example of d, let's say we have d of t2 minus d of t1 over t2 minus t1. Well, if we're looking at one instance, that means t1 is equal to t2. So if we were to plug that in, we would end up getting 0 in the denominator, and we can't divide by 0. So that's the main reason, can't divide by 0. It says, how can you estimate an instantaneous velocity? Well, instead of trying to find the exact instantaneous velocity at a certain point, we can estimate it by using a small time interval. For example, let's say we were trying to find the instantaneous velocity at t is equal to 5. Well, we could use the interval 5 to 5.001. Okay, notice if we were to plug that in for t2 and t1, we would not be getting 0, but instead a very, very small decimal, which would then help us estimate what the instantaneous velocity would be at that specific t value. Okay, so let's look at an example. Example 1 says, if you climb to the top of Tower of Pisa and drop a coin to the ground, and estimate the instantaneous velocity at t is equal to 0.7 seconds using Galileo's formula of s of t is equal to 16t squared. Okay, and then it wants us to compute this over the intervals. So if you look off to the left where I have Desmos open, I'm going to show you where they got 22.56. Well, what they did is they first typed in Galileo's formula. So they typed in S of, trying to find where my parentheses are. There you go. S of t is equal to 16t squared. Oops, I didn't write that 16 there. 16t squared. Okay. So if I click enter here and then I type in S of 0.7, I get 7.84, and then if I type in S of 0.71, I get that 8.0651. Well, if I actually take these values, so let's see if I can do it like this. S of 0.71 minus S of 0.7, okay, divided by, and let me get back, I wanted this whole thing. Let's try putting, there we go, this in parentheses, divided by 0.71 minus 0.7, I get the 22.56. So what they're doing is they are creating this formula here of S of T2 minus S of T1 over T2 minus T1, where this is T1 and this is T2 for all of these time intervals. Okay, so I'm going to go ahead and repeat those steps. And if you want to try on your own on Desmos, I would do that and make sure you're getting the same numbers as me. Notice that as our intervals get smaller, so they're getting closer to that 0.7, we're getting a more accurate representation of what instantaneous rate of change is at t equal to 0.7 seconds. So as we're getting closer here, this is actually a great representation. So we could say that the instantaneous rate of change at t equal to 0.7 seconds is approximately 22.400 feet per second. Okay, the next part says the study of rate of change is fundamental to the study of calculus. So we're going to look at the graphical representation of velocity. So it says average speed or average rate of change is represented by the formula below, right here where we have the change in distance over the change in time. Graphically, that is the average speed is the slope of the secant line. So if we were to look at a graph, we would have to look at 2 points on here, connect them, and that line we just created is called the secant line. And we would identify those points as 1, 3 and 4, 4. And in order to estimate the average velocity or the average rate of change, we would be using the slope formula. So 4 minus 3 over 4 minus 1, which gives us approximately 1/3. If we needed to calculate instantaneous rate of change, graphically, in order to do this, we use the tangent line. And when using the tangent line, you're only given 1 point of that graph, and you have to estimate a second point on the graph. So if I was to use that first point, which is 2, 4, and my estimated point, which is 5, 6, and let's call this point D, okay, I can then use the slope formula to calculate my approximate instantaneous rate of change. So this would be 6 minus 4 over 5 minus 2, which gives us 2/3. Now let's look at example 2. Example 2 is talking about a spin class. So what this is saying that as you're taking the class and the class is ending, as you stop exercising, your heart rate will decrease. Okay? Let h of t represent your heart rate, and then we're looking at the rate of change from 0 seconds to 90 seconds after you stop exercising. So what it wants us to find is the change in h over the change in t. Well, we could say this is h of t2 minus h of t1 over t2 minus t1, and we know that T2 is 90, so this is h of 90 minus h of 0, which is T1, over 90. And since we don't have any other information to try to solve this further, we would just leave it as is. Okay, example 3. In example 3, we're talking about a hypercoaster. And we're talking about wanting to create a new design for this hypercoaster. And in doing so, they give us this equation here, where d of t is feet and t is time in seconds. So it wants us to find the average speed or velocity from 2 seconds to 8 seconds. So again, in order to do this, we're going to have to type this in on our calculator. And again, we're using Desmos. So I am going to go ahead and change this to d of t. Okay, so that is 1.87 t cubed minus 20.64 t squared plus 112.79 t plus 132.56. I'm going to hit enter here. And then I'm going to just type in my equation of d of 8 minus d of 2 all divided by 8 minus 2. And that gives me my answer of 63.47. So I would say that d of 8 minus d of 2 over 8 minus 2 gives me approximately 63.47 feet per second. And then on part B, I'm going to do the same thing, but now I'm using 4 seconds and 6 seconds. So this would be d of 6 minus d of 4 over 6 minus 4. And I would approximately get 48.51 feet per second. And of course, I highly recommend you try this on Desmos on your own to see if you're getting the same thing. And then in part C, we're going to do the exact same thing using this time interval. And we're going to be plugging in these T1 and T2 values. So T1, T2 into D of T. Okay, so in doing so, we get 47.3997, 46.7142, and 46.6474, of course, all of them being feet per second. And then remember, as we get closer to what we were trying to find, and that is this exactly 5 seconds, so the instantaneous rate of change at 5 seconds, as we get closer to that value, this is going to be the most accurate, so the one that's on the bottom of our table. So we would write the instantaneous rate of change at t is equal to 5 seconds is approximately 46.6474 feet per second. And then part D wants us to write this in terms of the problem. So if you look at what we did right here in part C, I kind of shorthanded everything. Okay, I didn't write a complete sentence. I didn't talk about the hypercoaster. I just wrote a quick mumble jumble of words that's going to make sense to me later on when I go back. But let's say I need to make sense to someone else who's trying to look back at my work and read what I'm trying to say in context of the question. Well, in order to do that, I would just rewrite this in a complete sentence. So I would say the rate of change in the drop of the hypercoaster at t equals 5 seconds is about 46.647 feet per second. Okay, and then lastly, we're going to look at number 4. And number 4 is talking about airport departures. So when going over this in class, a lot of people were confused about what that means. So let's say you're going on a trip, okay, and you don't want to pay for an Uber, so you ask your parents to drop you off at the airport, okay? Your parents drop you off at the airport, and then after they see that your flight has departed, they start leaving. Okay, my baby's safe in the air. I can start going back home, okay? What that time is representing is 0 to 30 minutes here, okay? So they're waiting between 0 minutes. Okay, I just dropped you off at the airport. I know you're good, bye. The 30 minutes, probably waiting to make sure your flight has left, that, crying because their baby just left them kind of thing. Think of it that way. So V of t is this function here. Okay, so on Desmos, what I'm going to do is I am going to type in that equation. So I have V of t is equal to 92 minus 15 sine of t divided by 3. Okay, and then again, I'm just double checking on my settings. This is in radians because I am dealing with the trig function, so I need to make sure that's there. And then I can try to zoom out and see, and there is my beautiful sine function there. Okay, so writing this on my paper, V of t for t is equal to 18 means I'm plugging in 18 on Desmos. So V of 18, oops. And I get approximately 96.1912 vehicles per minute. Okay. So let's see here. Part B says make a sketch. Okay, so looking at the y-axis, that's V of t. So this is going to be my vehicles. And then t is going to be my time in minutes. And since this is in minutes from 0 to 30, I'm going to do 10, 20, and 30. And then to try to find where my graph intersects that y-axis, I could just click here. And notice that 0,92 pops up. So I know 92 is going to be somewhere where I'm starting my sine function. Okay, and then again, just zooming in to kind of see where it's going. I know it's going to go down between 0 and 10, up over 10 and 20, and then down between 10 and 20. Sorry, 20 and 30. And that's my graph. Part C says, what is the average rate of change over the time interval 15 to 20? Well, here's 15 and here's 20. So looking at this slope here, you should be able to tell that this is a negative slope. So that means our answer, once we find that average rate of change, should be negative. Okay, so you would plug that into your Desmos exactly like we did on the other problems. And you would do V of 20 minus V of 15 over 20 minus 15. And this would give you approximately negative 3.9992 vehicles per minute. And what that is saying, that 15 minutes, between 15 and 20 minutes after departure, there is about 4 cars leaving the airport every minute. Okay. Part D wants us to then find the instantaneous rate of change of vehicles at t is equal to 18. Remember, in order to do that, we have to look at these time intervals here. And you would do exactly what you did on Part C, but plugging in these new T1 and T2 values. So after you do that, you would get negative 4.823, negative 4.803, and negative 4.801, making this last one be the most accurate because it is the closest to 18. And again, this is vehicles per minute all the way down. So we would write that the instantaneous rate of change at t is equal to 18 minutes is decreasing, because they're all negative, decreasing at a rate of about 4.8 vehicles per minute. And then lastly, part E says, why can't the instantaneous rate of change be calculated like we did in part C? Well, recall when we were looking at the very beginning, that would be us doing V of 18 minus V of 18 over 18 minus 18. Well, this is 0 over 0, and that numerator doesn't really matter, but this does. And so the answer to this is because we cannot divide by 0.